It's a wonderful start for the year to come. So, Professor James Pustiejowski from Brandeis University is a well-known scientist in several fields of linguistics and especially semantics. And his relations to our institute are also quite good, I would say. And up to date, we are in one project, as far as I understand, right now. So I'm very happy that we can welcome him at this seminar. And his talk, as you see, will be on multimodal representations for natural language, meaning which is quite a topical topic, I should say. So, the floor is yours.
Thank you, Eva. Welcome. Thank you for coming out on such a gray day. I guess it's been kind of gray the entire time I've been here, but nevertheless, it's still beautiful. I should just mention that Eva introduced me at my first talk I ever gave at a conference, and the first thing she said was that I always mispronounce my own last name. So that was the way she introduced me. She pronounced it correctly, which apparently is not Pustiejowski, but something else. What I want to talk about is work that we've been doing in my lab for representing language meaning in the context of communicating with computers. This is an outgrowth of work that we've been doing that I've been doing for a number of decades, really, on semantics and computational linguistics, lexical representations, compositionality, lexical resources. And this particular project is called Communicating with Computers. It's funded by DARPA. It involves a number, probably about 20 different universities in the United States, as well as Europe and in the UK. Which is no longer part of Europe, apparently, and including Stanford and CMU, Colorado, Washington, Illinois, Brandeis, and Harvard. And the goal here that Paul Cohen has put forward as the program manager is as follows. And so I'm going to frame my talk on representing language utterances in the context of this work. I think it kind of helps establish and ground the approach that we're taking. It doesn't have to be put in these terms. It could be done from a purely semantic or computational linguistic point of view. But I'm framing things in terms of this interaction that is the guiding role for this program. Am I talking okay? Is it too fast? No? Fine? Okay. So the goal in this program called CWC, Communicating with Computers, is effectively to do joint problem solving with a computer. And that might be something that you imagine you're familiar with, or the normal everyday individual would be familiar with talking to Siri or Alexa. But as you know, those are all smoke and mirror interactions. Actually having an intelligent communication with a computer is what we do when people on the edge of artificial intelligence working on spoken language and generation and understanding systems, NLU systems. And so the idea of having a joint goal of building a four block tower, or building an arch, building a stairway, any type of joint activity, these are all very simple blocks world scenarios, are actually outside of the realm of what we can do currently in computational linguistics and combined with planning. Planning, of course, in AI has long had the ability to test options for the optimal path to select to achieve some sort of goal. But in the context of actually communicating with a computer, a human, and a computer being co-interlocutors, this is something that really has not ever been achieved. So the goal of this program is to do this. And one of the key aspects of this is to find out, in order to communicate, what are the basic building blocks that we share or we can share with our computer partner. And you might think this is trivial because this goes back to the issue of primitives and semantic components, factors. To a large extent it does, but it forces you to think in a new way about interactive modes and modalities that are not really part of the baggage or tradition that goes back to the 50s and 40s of what we took to be semantics. It does, however, force us to think in terms of working with people in vision and robotics and gesture and multimodal interactions with pads and phones. And so the notion of multimodality really comes to the fore with this type of interaction. So the goals of this program, as stated here, it seems trivial, but it's really, really something that's not been focused on in our community, is to communicate with a computer and have a computer come back and communicate with us in a cooperative way, not to answer questions from a database, not to be responding with a formatted statement from a question tree in an airplane dialogue for buying tickets, but rather something which is really cooperative and exploratory. So this involves quite a bit of extensions of what we've thought about in the past. So here's one example. I have two contexts, an A context and a B context. And in both of these, in either of these contexts, I might tell the computer, or the computer might tell me, add a block. And what's interesting about this is we understand a lot of ontological information and attributes associated with the structures associated with each of these situations. One, in the stack, we understand that extensibility in the notion of what add is actually doing in terms of extending an object is only available at one point, namely the top. For a row, we understand that the notion of extensibility is available at either end. So what's interesting is we know something really quite complicated and complex, and we have to sort of represent this in a language that the computer can understand, or help perhaps teach the computer to understand that there's this notion of a scalable, extensible object, and where there's a hot spot for something like adding, and that stacks have one because of the physics of the table, and rows have two, a cross might have four, and so on and so forth. So this notion of an extensible object is already by itself an ontological object, which is outside of the purview of conventional interactions with computers. So it's really quite sophisticated. So the goal and methodology in my lab, now it's kind of a lab, not just a group, because we actually have quite a few people working on experimenting with mining images and mining movies in order to automatically learn activities, but also still doing fairly detailed semantic modeling. But now not just in terms of ontological and lexical semantics, but also in terms of visual semantics. So the goal is basically simulations, multimodal simulations. And I'm going to try to motivate why simulations are such a critical component to two things. One, communicating with computers, but also as a way of essentially having a richer representation of models for natural language as well. So a simulation integrates multiple modes of communication, linguistic and visual. To be precise, in this context, we're working on integrating musical forms with language and visual as well, but we haven't had any results on that just yet. We assume, as would most people in the field, that models of semantics have to be extensible. They're generative. And I'm going to have something that I'm going to call a communicative act, which is going to be an extension, kind of a generalization of a sentence or an utterance. So no longer will I just say, put a block on the stack or move the block, but I might have a communicative act which combines the spoken, the gesture, maybe a picture, maybe just context as well. So we'll just call it a communicative act. This is not a new idea. This goes back to the 60s, of course, but I want to bring this notion back up. Now, what I think we need to think about is the following. We've thought about compositionality for linguistic utterances. We've thought about compositionality for visual constructions. In vision, they think about composition. Now we have to think about compositionality, whether it exists, but it certainly should because it's computationally an extremely attractive approach to take. Compositionality of all the components that go towards making a communicative act. So gesture, language, facial expressions, and just context, as well as perhaps other sorts of visual clues. So compositionality is something we want to strive towards, and we'll have the same types and the same compositional mechanisms, and hopefully the same parsers that we have in language. Another thing that I want to mention is that models have to be embodied. Now, embodiment is this, you might say, a bugaboo term in English, where you have people in cognitive linguistics from California sides of linguistics doing embodiment. And that's all well and good, and it's actually not a bad approach to thinking about semantics, but we want to operationalize the notion of embodiment and make it formal, which means coming up with procedural and operational and maybe even denotational models of embodiment. And I'll talk about what those would be. So the goal of our work is to state that one of the more effective means of communicating with a computer, or for a computer to communicate with a human, sets of humans, would be through a simulation. Not through giving me the results of a minimal model that I've generated, or a theorem proving, or some sort of set of results of a proof in a sort of RDF triple proof store, rather through a simulation. Now, we have to admit that formal models provide reasoning platforms, which are undoubtedly useful, and we use them. Minimal finite models enable inference, but they are not an effective medium for communicating. So we're thinking about the medium for communication. Communication for humans and your pet, my dog, or for computers and humans, is facilitated through some semiotic structure that's going to be shared and understood by both partners. And so that shared, understood communicative platform is going to be a simulation. And these simulations are going to be embodied representations of situations, of events, and the participants in the events. So we're going to think in terms of image schemas and visualizations of actions. These are core human competences. We understand actions and the participants just intuitively. So why not have the computer talk to us in terms that we understand intuitively? So we're going to basically force the computer to think closer to the way we visually conceptualize and understand the world, as opposed to forcing us to think in terms of description logics or RDF triples. So simulations are going to be visualizing context. So what's visualizing context? Well, we think about Barcelo and other people from cognitive psychology and the notion of a prototype scenario. But as Larry Barcelo has pointed out for 20, 25 years, along with others, the notion of a prototype is context and situation dependent. So I don't have a prototype of an eagle, I have a prototype of an activity associated with an individual eagle. So this is a flight, this is a perch, I might have a nesting. More to the point of, say, for an artifact, what do you think about the prototype or the default of a pencil? Now you can have an atomic ontological type for a pencil. It's some sort of artifact, it's got a function, and it's a supertype of a physical object. It has some constitutive quality, maybe it has some wood, it has some kind of graphite, et cetera, et cetera. What we want to understand for how to actually engage with an artifact is prototypical situations. Here's a pencil in a cup. Notice it's vertical. Here's a pencil in a drawer. It happens to be horizontal. I might have a deep drawer that I could have a vertical cup, but this is my computer desk drawer. And this is my writing with a pencil. So context is, I'm going to argue, part of the semantics of objects that we use and part of events. Is it part of the lexical semantics? Probably not part of the typing, but it might as well be part of the information we carry around we encode, we cache as the prior information. So it's something that we can learn from enough data and create language models associated with the data that would be the behavioral attributes of objects. And that's, of course, what we're trying to do by mining videos and images associated with lexical items and generated captions of images, as are other people with visual semantic role labeling. Now, in these three examples of the pencil, we have a verticality associated with how it's supported in a cup, something being horizontal, being supported in the drawer, and some kind of diagonal, non-vertical, non-horizontal for it being used in actual use. And this is, in a way, not too different from word sense disambiguation. We might think in terms of object situation disambiguation. I want to be able to disambiguate the contextual meaning of an object denoting word to the appropriate situation. So, and this, of course, is what several groups around the world are doing. You want not just collocates of those lexical items or phrases associated with a particular word to give you n-gram or mutual information associated with the lexical items associated with pencil, but also the visual n-grams associated with that as well, if we're thinking in terms of language modeling, which we can. So what we want to go towards is a way to represent a simulation of an action that's carrying information about a mental model, but is computationally tractable and is not that far away from the types of resources we have to make something usable for purposes of generating simulations and understanding language that would come from a computer or for a computer to generate to a human. Mental models go back a long way. Johnson Laird talks about Craik's original proposal in 1943, this notion that we carry small-scale models of external reality in our head. Johnson Laird's own representation of mental models, of course, is well known. And then Dedra Gentner and Stevens and others have proposed human knowledge models for capturing domains, et cetera, et cetera. Now, let's just look at more specific information associated with what's involved with simulation construction or scenes. And this basically exercises a lot of information, a lot of logics that we've dealt with in language understanding. Temporal relations, such as the Allen 13 relations. Spatial relations coming from the RCC. This is all from qualitative spatial reasoning. Work in semantics. There's work on static scene generation. That's Coyne and Sproat's work, and Jeff Siskin's work on static scene generation. And then Chang and others from the Vision group at Stanford have looked at generating static scenes. But there's another whole tradition from qualitative spatial reasoning and gaming AI, which uses scenario-based simulations, such as Ken Forbes's work and Gentner and Forbes and others like that. Okay, now, so what I want to start now is to build up what we want a simulation to have as properties. It's going to basically be a minimal model, which we're going to generate from linguistic input under a number, and we're going to add to that, not just linguistic, but also gestural and other things, under a number of agent-oriented cognitive constraints. And these are going to be an epistemic condition on the agent, so we're going to have a point of view. So we're going to imagine that a simulation is not just a top-down, bird's eye, God's eye view of the world. You can do that. But we're going to imagine an epistemic perspective that if I'm going to simulate simulate someone talking to a group of people, interested, quote-unquote, listeners, or at least listeners, then I'm going to simulate a point of view. I can take my point of view. I can basically turn it around to take yours, whatever. I'm going to encode a perceptual logic, a hybrid modal logic, which allows me to basically pan around, not just quantitatively, but qualitatively as a modal logic, to give me the epistemics associated with your perspective, what the enveloping embedding space is, et cetera, et cetera. This is important because we want to know how much simulation to build. What's the necessary embodied embedding space, it's called. How big is the space associated with an event? How big do I have to make the R3 region in my simulation for you to actually be hearing me? Does it have to be just the convex hull associated all the way up to the tops of your heads and me? Or does it include the enveloping space of the hall, et cetera, et cetera? These are important issues for simulations. So one of the assumptions we're going to make is that objects have behaviors. Sure, everyone knows this, but we're going to try to actually build them into a computational treatment. And roboticists have been doing this for 30 years to varying extents, usually extremely procedurally oriented, never too interested because they never need to think about how to map something to a denotation, because why do they care for models, right? They just want something to work. If you want to start talking to the robot or talking to an arm or something, you've got to have something that's not just a procedural and operational semantics. You've got to have something that actually coordinates and talks to the semiotics of the linguistic system. That's where you need denotational semantics. Affordances are going to be modeled dynamically as events. So you're going to see a lot of event-type Aktionsarten, a lot of standard kind of semantics now kind of brought into the service of building simulations. Behaviors have agents. So we're going to make this distinction between what we call object models and action models. And together, composed together, they'll make an event. We want to separate them out formally for reasons that I'll tell you in a second. Then we're going to introduce this notion of a habitat. So things happen in context that are really quite complicated, at least more sophisticated than denotational semantics ever assumes. It's not just watch prime, but actually has a particular configuration, has a particular orientation, has a situation. Its embodiment is on my wrist, et cetera, et cetera. So there's configurational constraints which must adhere in order for the watch to be satisfying its purpose, its telic role, its Gibsonian affordances in the appropriate fashion. So we're going to start with a vocabulary of logical types, and we're going to have the ability to build up larger types, and then we're going to have larger and larger events as a conventional sort of inductive or recursively typed system. So I'm going to, not probably too surprising, start with some basics from Generative Lexicon. It's a useful stepping stone because it's kind of template-based, it's frame-based, it's not too dogmatic in typing. You can basically have a lot of different typed interpretations of it, all the way to Asher's Martin Löf type system. And then we're going to need some dynamics. So you're going to have to make things unfold in the process. So you need a kind of dynamic semantics. So we've got our object semantics. We've got what are we going to take the object to mean? What is it going to have as its substructure? Events are going to have some structure, and we're going to put big things together. So just kind of a standard slide for what qualia structures might be for an object. I know its basic type. I know what it's made of. I know what its purpose is. I may know how it came about. This is just basic typing information. When you start doing simulations, these things actually become kind of important. It's not just sort of a flag you fly. It's actually something that really is it's an interesting signature or handle on the type that you're actually going to be working with. And in addition to this, though, you got to get off the ground. You can't just deal with words. You got to get something that's going to have a visual representation. So we've created something called VoxML, which is a visual object modeling language, visual object concept modeling. And these are essentially the geometric projections, if they have them, of objects, of nouns, verbs, adjectives, quantifiers, adverbs, functional terms. So we're going to take objects to be entity classes that have geometries, or don't. Anger will not have a geometry. It will have a situational construction, which is not going to be a classic sort of geometry. We'll talk about abstract nouns in a second. Verbs are going to be programs. They're going to be n-ary predicates that take objects and other evaluated predicates as arguments. Logical types, you're going to have attributes, relations, functions. They're going to be all predicates which take objects as arguments. And we'll talk a little bit about how they evaluate the states, and functions evaluate the geometric regions. So these entities then have a compositional logic of themselves. So VoxML will have a compositional semantics by virtue of its type structure, which will create the composition of a scene, and that's going to be called habitat composition. And that's going to be from language to a visual representation, composite by types. And you put these things, we're going to call them a voxeme, that's going to be like a lexeme, and you put them together into a voxicon. And if you go to voxicon.net, you can see some of the initial products of this. Our goal is to eventually, I'll talk about the goals later, so to link to VerbNet, and which we are doing with Martha Palmer right now, and to link to the types that might be associated with CCGs and dependency parsers and things like that, actually coming directly from the visual typing. So what's a voxeme? Well, a voxicon is going to be a library of voxemes encoded in this VoxML language, and it's going to have the object geometry structure, which is going to have its formal object characteristics. It's going to have this notion of a habitat, which is going to be a way of embodying and embedding an object, which is going to be its orientation, its situation context. So I can have this is empty, right? I can have a cup. This is just a cup, regardless of its position, and I can do whatever I want to with it. I can store them so that I can bring them out for parties. It's a cup. It will always be a cup. It has a kind of global modality. So, but that's not its orientation by virtue of its convention, right? So Gibson would say its affordance is not ready. It's not being satisfied. This has water in it. It's doing everything it should be doing. It's doing what it was designed to do, namely hold something that would be then affording me to take from it, right? So that's like the qualia. That's like the telecurl, right? So we need to encode that kind of information because you want information to be carried with the object. You want the object like in a game, right? World of Warcraft or whatever it might be, but we're talking about our simulations. You want the objects to have their own knowledge about what they do. Everything in a simulation is an actor. Everything is an actor. You know what to do. I'm a cup. I know what to do. So currently we have 3,000. Well, we're going towards 3,000 object voxemes, and we currently have about 512 geometries. 200 have complete affordances, but 40 verbs, which are now encoded as programs, and we only have 3 rigs, three guys in the simulation called animated models or rigs. And I'll tell you about those. So the concepts are what you might imagine you would have to have if you're going to look at the visual or 3-dimensional representation of semantics. We have an embedding space. We have something called the minimal embedding space, which is what I was just talking about before. So just to kind of wrap your head around this, I'm looking at my computer. I'm looking at a book. I'm looking at my phone. There's something that they all share, but they all have very different values of. Namely, they share a certain type of embedding space. There's what's called the affordance space of my being in a particular orientation to the screen. So the book has a screen, as it were. It's a neutral screen. A paper book has a screen. I have a phone and I've got a computer. But the affordance space, and then therefore the embedding space to build the event, is different for each case. Okay? So I can be on the tram, the 22 tram, looking at my phone real tight because it's very crowded. It's a very small space. I can be here or here and so on and so forth. Okay? And you are actually treating me as a big screen. So essentially, there's a 2-dimensional projection of me, codimension, which essentially is a screen. So these all share the same sort of affordance space. You're viewing something. We need to look at the various axes, locations, orientation, the vector denoted by a particular axis, and so on and so forth. So let's just look at an object type. So this is going to be the type structure for what builds a controller, a watch, a cup, a block, a rock, whatever. You're going to have something that points to its ontological status, which is going to, let's say, be a type structure in whatever, LKB, GL, it doesn't really matter, okay? Some sort of ontology. It could be, and it could be Dolce. It had to be a Dolce type, okay? And then I've got the type structure for the VoxML itself, which has got this notion of a head, which I'll talk about in a second, and then its components, whether it's concave or convex, rotational symmetry, reflectional symmetry, these things which are important because of the way you can interact with something and because of the way you will identify and understand what something is depending on whether it has those properties. So they're basically like the qualia structure for the VoxML, okay? Then it's this notion of a habitat. How is something situated intrinsically, and then how is something conventionally situated? So I might have a habitat for a cup, which it has to have this particular orientation, which I can encode, which affords it to contain something, which could be water or sand or whatever. This is a perhaps habitat, an orientation for putting it into a dishwasher, maybe for cleaning or for stacking. So there's all kinds of things which might conventionally be associated with an object, and you learn those, okay? But this is the call it the analytic orientation, by virtue of what it's supposed to be doing. And then it's embodiment. I want to know what's this relative size. So this is actually just kind of a nominal scale, kind of an ordinal scalar structure. I don't need to know exactly how big something is, but I want to know that it's smaller than I am. It's maybe 1/10 the size of me. But also importantly, we're going to start later on, we'll look and see how scalar, the notion of embodiment is that if something's graspable, then it's by virtue of the definition of graspable fitting into my hand, okay? These are important ontological notions. Okay, so an affordance is the context being associated with something such that every time I do something, something's going to result. So this is a first-order dynamic logic expression. It's a dynamic or a quantified modal logic expression where I have a context, and if it's satisfied, then every time I do something, then some result's going to happen. So you start off with some kind of really simple notion of event structure, and like state-to-state transitions, the iteration of some change of a location of an object. You iterate over that, and you have like a process or an activity, and then you have what might be called a derived transition. The bottom thing is you layer, it's like a cartoon structure for events. You have a notion of changing, continuing adding to something. Eventually at the state, at the final state, I might have something which I would call a arch or a house or whatever, a 5-block stack. So events as programs is this dynamic interval temporal logic that we've been developing for about 5 years. And it basically takes the normal syntax of dynamic logic with a first order, a fragment of first order. And so the idea is that programs are basically encoded as these diddle constructions. And so the idea of putting A on B is given that some context is satisfied, and then while I'm doing something, then I'm going to do something, and then the final condition is going to hold. So this is essentially an operational that has denotational interpretation of a plan from the 80s, but with a lot of nice twists, which is that it's got a defeasibility aspect to it, and it has some very nice computational properties, which we can talk about. So directed motion, this is just to look at one dig down slide, is if I'm just going to talk about moving this over to the edge of the table, I'm basically just testing the location of it and just continuing while it's not at the end of the table, and then the satisfaction conditions are going to be satisfied, and then I stop, okay? We need to have some way of talking to the simulator, and the simulator is written in C#, and I need some language, the interpreted version of this Python program, which is going to be able to render this in Unity. Okay. We represent these for purposes of parsing as event dependency graphs. And so events are basically word sequences. And so as such, you can label the dependencies between words as a syntactic dependency structure. You can group events, just as you do in your own dependency structures here in Prague. You have 3 dependency types. The actual program, which takes you from one state to another. The test, which is going to be the thing that holds during a transition. And then the content. It's what's holding in my particular little state. So I have this thing over here on the left, which is an unguarded transition, and then the other thing is a guarded transition. And these are just basically examples of like the ball sliding. You can have more complicated examples from something like bioinformatics, like a protein activating another protein, and so on and so forth. Okay. So programs have this VoxML representation, which effectively, they point to a GL dynamic interpretation, but they also need to build something in the simulation. So they are programs that actually take advantage of the semantics of the objects that they're involving the participants, and then they have to go render this stuff. So slide is going to be this thing which takes as arguments. It's going to have then in this body the event structure of I'm going to be grasping something, and while I'm holding it, I'm going to be making sure that there's this external connection between the thing that's being grasped and it's going to be moving, and I'm going to be moving it. So that's a very simple example of that. And flipping is going to be changing the orientation, and pushing, and so on and so forth. I'm not going to get to the details of this. We'll see that in the demonstration. Functions are just going to be functions as in any kind of functional language. It's going to be a whatever, domain to domain object. So it's going to be type to type. So I'm going to take the top of a flagpole or top of a desk. It's just going to be the codimension, right? N-1 of the thing. It's going to be one-dimensional or two-dimensional or whatever, and so on and so forth. Okay, so let's get to the point. Habitats encode context. Let's figure out what this habitat is. So a habitat is built by placing it within a minimal embedding space called its local embodiment, and you're going to contextualize it. And that entails activating two things. What's called the Gibsonian affordance, if you know James Gibson's notion of affordance, and then the telic role, which is what something's for. And I'll explain the difference between those. So a table, the top has to be oriented upward, the surface has to be accessible, and so on. So you can have a table stuck in a closet, right? And it's still a table. But it's not a usable table because it's got another table stacked on top of it for purposes of putting them away. But in order to use the table, right, you gotta make the context associated with it. So the context has to be activated in order for you to actually do what you do with the table, right? Now the notion of a Gibsonian affordance is this thing's graspable, it's throwable, I can move it, right? That doesn't talk about its intentions, what it's for. Similarly, in order for me to drink from this, if I'm not going to use a straw or some kind of other sort of camelback thing that I use while I ride my bike, I need to be able to grasp it, to pick it up, to hold it. Those are the Gibsonian affordances. Then the telic, the normal things that we would think about as purposes, is to drink out of it. It's holding something for me to drink. So it's like a chain of different activities. Okay, so that's, and you're familiar with affordances, I'm sure. They've been around for 30 years. So here's an example, a specific example of a plate. A plate has, unlike a piece of, like a sheet, like a cutting board or just a piece of wood, a plate actually has a little bit of concavity by definition. And so you have to define the concavity, the orientation of the concavity, and then the rotational symmetry, the reflectional symmetry associated with that. And then basically you've got these affordance structures, which say, okay, if it's in this particular orientation, then I can put things on it, it can hold them, and so on and so forth. Interestingly, by virtue of a plate, if it happens to be circular, for example, a particular reorientation will allow you to actually kind of roll it, right? So you can roll a plate if it has a particular kind of orientation being satisfied. You get the idea. Here's the notion of a head. So a spoon, say this is a spoon, this is the little, so cup. If you take a spatial logic like von Bentham's spatial logic, where he talks about spoons, you've got a stick and you've got the cup, right? And here we have the same kind of structure geometrically. You've got some sort of one-dimensional object, and then you've got a cup. Okay, and the cup is the concavity. Okay, so this is just a classic GL representation for stack. What a stack is, it's got a bottom, it's got a top, it's got a mid, which is potentially null, and basically the difference here is that now I'm starting to think about how do you build a stack? What do you do to actually build a stack? And this looks kind of procedural, almost it's operational. And here's the VoxML for a stack. So this is the visual rendering code, as it were, but denotational, for what a stack is. It says, okay, I am a scalar object. Remember the first slide I showed was a row and a stack. And they're called scalar objects because you add something to it, to a stack, and it's still a stack. Yeah, right? It's like a group, right? Groups. So we have these collections or ensembles, and it's yes, they can be philosophical paradoxes, but from point of view of group objects, it's important to know that once I've got an arch, I have an arch, and I can't really add anything to an arch to make it more than an arch. It's an arch, and I'm putting stuff on top of it. But a stack can continue being a stack, and a row can continue being a row. So that's an ontological type that's important to distinguish. And so what's interesting is that add as a verb, as a program, basically says, I'm going to go and find the hotspot for the thing that I'm adding to, and that's called the extensible location. It's a function. The extensible location of a stack is this little part right here. The extensible location of a row is going to be one of these 2 points, etc. Okay, so it's ambiguous. So, and that's so like this is what I'm saying here. So, I have 2 ends to a row. I have a top to a stack. So, the notion of extension basically explains this, but I've got subtyping on what the extension might be. Okay, let's go to the actual simulations. So we have a simulation environment, experimental environment called VoxSim, which we experiment with. So we do completely constructed simulations, and we also do Monte Carlo simulations, where we take the averaging of information or the generation of what we take to be the normal of an unspecified value for a variable that we don't really care about or is not critical. And this is our simulation testing environment. So we do a dependency parse, a classic dependency parse of the input. We extract the labeled entities in the scene and basically do a diddle semantics of that, the dynamic interpretation of that, and which translates it into the program object and some kind of relations. So if like put the spoon in the mug, for example, we resolve the parse sentence into this form, and then we basically puts us into a context where we then render it visually in the environment. So as I mentioned before, the events are modeled as an object model underlyingly, which is a state-by-state characterization of the object, an action model, which is the actor's motions through time, and then the event model is going to be the composition. So if you know dynamic logic, you know there's no such thing as causation in dynamic logic. And in fact, in most update semantics, causation is not really a primitive, but something has to be construed from situational observations. So in order to model the notion of caused motion, for example, I put the controller over here, right? We have to do something different, which is actually something I call rig attachment, and I'll describe that in a second. So caused motion creates something called rig attachment. You link the motion of the agent to that of the affected object through a rigging. So this is a rig. I'm a rig, and basically all the way down to my fingers. Has a semantics to it. Basically, I attach the thing that I'm moving as a daughter, and then we move together. So I only have to keep track of one motion while I move. So there's no causation. I'm just moving the arm, okay? And the arm happens to have this as the daughter, the terminus daughter. And that's, so physical force as a model is virtual rigs. So gravitation and other sort of force dynamics are actually virtual rigs, kind of like a Cartesian vortex model from 1660 or something like that. And you actually have so it's a virtual rigging pulling back. So the gravitation is actually a rig pulling here. Why are we doing this? Gaming systems and simulations have physics models, right? You can just program something in and your gaming system will make it fall over. Well, we don't want that to be our semantics of it. We want a qualitative understanding of what's going on in the physics. So we're creating these sorts of qualitative, what we call cognitive physics, models to understand how they're actually talked about in language, because the way something's talked about in language has nothing to do with the way it's rendered in a visual system, in a simulation. So here's just going to start giving you some examples of, so this is the interpretation, put the spoon on the mug. I have an orientation where on is actually satisfied. So what's going on here is I'm interpreting the linguistic expression, turning it into the dynamic interpretation, the diddle, and then creating this voxML representation, which then renders it into unity. What's interesting about this is that on is creating this top lamina of the mug such that it's going to be in a support relationship. In, on the other hand, will require me to orient the spoon such that it will be enveloped mostly by the cup. As you know, it doesn't have to be complete envelopment because it's still sticking out, right? If I were to put that lid, I'm not going to show you, the lid on the mug and then try to get the computer to follow through and put the spoon in, it would not be able to because the conditions would not be satisfied, right? The preconditions for going into it would be closed or terminated. Let me just point out one thing here, which is interesting. Dynamic, so this is part of the dynamic update functions in the semantics of the dialogue. So is this visible? Now, what am I showing here? I'm showing that each individual block is a separate entity. I'm going to now stack the blocks. So stack has this one interpretation where I take a collection. I'm going to create a unit. And so I'm going to create this thing, and now I'm looking at it, and I have something which is reified as a stack, and I can move it as a stack. So it's now I've created a new object in the domain, in the environment. So by virtue of my actions in the context of the dialogue, I've created a new object which I can now refer to as it. Put another one on it. Okay? And this, of course, is just update semantics in discourse, but it's important to be able to render this and have this happen. So here is rigging an object to an agent. So here, this is just, I think I already showed some of this. I'm just kind of moving some things here. This is just the object model. And okay, here I have the hand. So now I've rigged it. And so basically what's happening, this is Diana, our one virtual rig. She's basically, as I said before, we're rigging, the rigged attachment is that the one motion is now capturing how we actually then create the simulation. Now, do I have like 5 minutes left or so, or 10? What we've been working on for the last 4 months is integrating gesture with a group that works on gesture at Colorado State University, Bruce Draper. And this is in the context of the CWC, but we want to actually start working with other people who've been doing gesture, like Matt Stone and people in Edinburgh. So what we're looking at is, given a simulation model, we want to have a generalization of what an expression is. We have a multimodal expression, and we want it to be now a function of the denotation of its component modal expressions. So we want to have a gesture, and we want to use the notion of preparatory phase, a pre-stroke hold, a stroke, retraction, and then ease, right, from the gesture community. Those are the kind of the steps that are at play in gestures. And then we basically look at the situational denotation of what the stroke would be, which might be a deixis. We look at the R3 region, and then the constraints satisfied within that R3 region that would basically point out that it's the yellow block or something like that. And so we're looking at, in particular, a small set of gestures, like 4 or 5 for now. Hand shape, so that we're not looking at facial expression, it's just hand shape. Palm orientation, finger orientation, hand location, and movement. So gesture is a function from configurations to configurations. Now, within the context of what we're doing in terms of simulating actions and language, gestures are really interesting because they're actually interpreted programs. So if I say I'm going to interpret James moving the controller, okay, so I do that. But a gesture in the simulation is something that we have to create an action for, a simulation for, but then it has an interpretation, right? It's a semiotic expression. So we create a gesture, which is a program, out of objects which are voxMLs, but it has an interpretation by the interlocutor. So it has to have its own semantics, independent of the actual extent of it as an event in the simulation. So, for example, a particular gesture might have as its semantics, like palm converge, has as a semantics push together. So the semantics of palm converge is to push something together. It's like this is our avatar. So what we're doing, we're focusing on head nods, right arm down, arms together, 2 arms moving towards each other, away from each other. There's a lot of different body part poses that I'm not going to go into because I don't have time. But the point is that gestures are interpreted programs. So in our simulation model, this is Wilson, because he looks like the soccer ball from the Tom Hanks movie where you got, the what's it called? Castaway or something? Anyway. So here's an example of Deixis Wilson pointing to a block. That's Diana, our other rig. This is kind of a side view that I've taken to be so that I can basically look at it. Usually we can view in the embodiment of Diana. And so Wilson is using a multimodal, is speaking, take that block and pointing to that block, okay? And pointing to a different block to add that block. And then basically doing a push, all right? And then showing a thumbs up when it's done, if it's successful. Wilson has a claw, which is going to be a claw and translocation, which is to pick up. And, okay, so let's see, I think I have, this is, okay, so this is, and these are all basically generated from the dynamics of the VoxML being used. And then, so the way we're interacting here is Wilson is telling us, and I'm acting as a human, to tell Diana to do this, because we don't have Diana understanding Wilson yet. Wilson is telling me, the human, and then I'm telling Diana what to do. So I'm acting as the interpreter for Diana. She's actually doing the moving. Come on. Anyway, whatever. I should just close up because I'm running out of time. These types of models are rather involved and difficult to create for obvious reasons. They're quite rich. So we're looking at high-level habitat acquisition through basically doing kind of multimodal word embeddings. And we have one grad student who's looking at the places data, landscape scene classification, and the Flickr 30K corpus, which is annotated with various types of descriptions, and creating scene type descriptions to model what the overall classification of something would be to give a high level habitat, and then use low level features to then start determining what the visual collocations would be for an object. And we're also doing event capture of videos, both from our own videos as well as a movie database to do learning of events. And I won't go into that. So, creating models of compositionality requires integrating gestures, facial expressions, situational context, and language. So the notion of compositionality that we've been dealing with since Frege has to, like the good semanticists from the 60s, like Donnellon and Kaplan and others, like they were saying, and a lot of people in the Prague School have said for a long time, that we need to be able to integrate not just the language utterances, but also our situation, the context, our gestures, everything, and see if we can build compositional models for those. Types, type inference, partial, structures like that. The way we're approaching this problem is to enrich some of the data structures and models that we have, such as qualia structure, event structures, by building habitats, more dynamic notions of models of events, like dynamic event models. The new addition to this, which we think is actually kind of independent of any particular theory, so it could plug on to any number of other types of platforms, would be VoxML, which we're creating as a standalone resource of a voxicon and an API to other types of renderings. The VoxML, I think one of the keys to VoxML is that it's explicating the affordances for objects and for events, which I think is something which has been really under-modeled and under-researched in semantics. Currently, we're integrating with the James Allen's TRIPS dialogue system from Rochester for doing clarification in dialogue. And that's it. Thank you for listening.
Well, thank you very much for your very informative and stimulating talk. And now the floor is open for questions, remarks, suggestions, whatever. Yes, please.
This is something which became very fashionable, and you're still following the traditional proper analysis way of research. So would you be able to comment on neural approaches to this? Because we are seeing the automated cars, and everything is apparently trained there. So they are not actually teaching how to.
Aren't they? So I don't believe in pure neural network approaches because they don't exist. When you go training, we do embedding, word embedding work in my lab, and so I'll just say some outrageous things just to get people upset. I don't think it's possible to do without actually bringing in our own notion of representation. So when you're actually training and adjusting and doing what's called the feature engineering, right? So in a multi-layered neural network, right, now the feature engineering is to get the right parameters and make sure you have the right number of layers and number of nodes, right, states. And it works beautifully well, right? And who's doing that? Well, if you have complex data and complex situations, it's of course the intuitions of the human who's actually the designer, right? The human, unfortunately, has these representations which we still don't know how to kind of unpack. And so, of course, I mean, that's not new, right? That Turing probably said that. But the point is, don't get swallowed up by the hype without recognizing that the representations are still there in the way that we go through training and tuning. So I'm all in favor. In fact, we need neural network representations in order to scale this. This is not scalable, right? As you might imagine. So representation, I haven't talked about the goal of the next phase, the next 2 years of the program, which is to integrate embeddings and deep learning, basically just conventional learning with more powerful networks, with these types of representations, and then see how we can actually do the scaling. So I completely agree that I have ignored the issue of learning, but I didn't really say I was going to talk about learning. I'm talking about conventional notions of representation, which are, I still think, there in representations in the way that we interpret the configurations of neural network representations. So we've got the actual, call it the implemented representation, and then you've got the intentional representation, which is what the human is using to create the extensional representation, which is the neural net configuration, okay? And the intentional is what I've been talking about all day today, or this morning. And I think unpacking what the intentional representation is in the process of how I actually then go and do this encoding and feature engineering is something that we're still learning how to do, right? We don't really know. And it's a procedure it's a methodology of making sure that I have a rich enough ontological structure in order to then put into the input as the input vector for a representation, for example. So, for example, the kind of features that we would have, the richer the model, for example, that I have for a linguistic utterance, okay, so language, the better the neural net models that are going to perform, right? I think that's true. So if I have, that's not false, is it? Right? If I have dependency-based information, maybe some configurational information, maybe even semantic role labels, and maybe even some discourse labeling, right? And then I put that into my vector, right? The notion of the embeddings are going to be richer because I'm capturing, okay, so where did those come from? That's the kind of representations we're talking about here. So you take it as a given that we have them, totally fine. But you got to build them. Where did those come from, right? And they come from this long, unfortunately still somewhat laborious technique and strategy of training and supervised learning and then semi-supervised learning, and then you can just throw it into a CNN or an RNN or some ComNet or something like that, right? And then you've got the stuff that makes it to Newsweek and the New York Times. What you don't get in the New York Times is all the people who are actually building those representations that then go into the vectors. They're the ones that should be heralded and given the Nobel Prizes because they're actually building these representations, right? See, the thing is, here's the thing. Sorry to go on about this, but I've been I've been doing this for a long time, and I get this kind of not pushback, because I think you're absolutely right. It's just we have to be aware that when Jelinek and others came, okay, now Fred even accepted this eventually. It took him 20 years to accept the relevance of syntax. But when we started doing statistical models for non-speech input, we just sort of assumed we had all this data and it's for free. What was it? Penn Tree Bank, the Dependency Bank, all this stuff. And where did it come from? It came from like 50 years of work, of not just people doing hand annotation, but theoretical modeling. I mean, lots and lots of work. It did not come for free. But you can download it, right? You get a zip file and you pack it, you unpack it and you put it into your SVN Lite or your LSTM Lite or something like that, and then it just kind of loads and runs. So I'm just saying, let's not take for granted the relevance of representation that then gives us the ability to build nice learning algorithms that will let us get to scale. And we need this. We need both, because I can't build these types of simulations to scale without having those types of robust things. Sorry, that was not a short answer, but...
Thanks. Yeah, I totally agree with your view. I think we definitely need both, and it maybe boils down to the question: what do you want to do? Whether you want to just pass a Turing test with your device, and in that case, you can afford to understand less what is happening and you can just train it. And if you want to understand what is happening, then you need.
That's a really good point. And let me just parrot or repeat what Paul Cohen, who actually is an AI person himself, who's the program director. And he said at the beginning, and he says this kind of every week or so, or every month when we meet, we're not trying to pass the Turing test, right? You want to pass a test where you can ask the computer, why did you come up with that answer, right? You can't ask Watson that, because Watson would have no way of knowing, right? It just basically took the best of the first 20 and best of some sort of argmaxing of 45,000 different classifiers, right? But you're absolutely right. And what Cohen thinks is a way of communicating with the computer is for the computer to actually be able to explain why it did that. Because you want to go to the next step. You don't want just an answer. You want to say, all right, well, what do we do next? Well, let's try this, right? And that's absolutely right. I totally agree with that.
How big is your voxicon now? And did you? Sorry if I missed something, but I assume it's now pretty small, isn't it?
Yes, it is. We've only got like 300.
Yeah. So, have you thought about expanding it using the never-ending language learner or something like that?
Yes, we've looked at that. So, Mitchell's a smart guy. That's not a bad approach. But it's not exactly what we'll need to adopt and modify the input. But absolutely, that's exactly the kind of continuous input, mining the contexts of different words as well as visual input. That's a good idea. We've looked at that. I don't have anyone working on that particular application. But yeah, that's absolutely the kind of thing. So the first things that we're doing for verbs is obviously to look at the lexical resources. Problem with lexical resources is what you might imagine. They're not contextualized, right? So, but VerbNet has, for example, and FrameNet to a lesser extent, has enormous utility in the linguistic information associated with it. And it allows you to do some bootstrapping. But the web crawlings and inductive learning that, for example, the never-ending learning, it's a very good resource to try to exploit. Yeah. As well as, do you know if they've done multimodal acquisition for visual to language mapping, for example, embedding?
Wasn't it some big number of tiny images? There was a project like that. Yeah,
that's right. And that kind of relates to the visual semantic role labeling of Luc Zettelmoyer and some of the people like that. Yeah, so those are really very useful projects and approaches to try to exploit. I just have to say I haven't looked at those to see how we might do that. But yeah, I absolutely, totally agree. So I have to answer that I haven't explored those enough, and the problem is to come up with what we're trying to do is to grow the lexicon in a fashion, the voxicon, in a fashion so that what we release is actually stable, usable, and not something that has a kind of airy quality of a lot of holes in it. At some point, though, you might have to say, okay, look, let's just wikify this. Let it be something which people crowdsource. And that's actually something we've thought about at some point. What do? You actually then have to let the citizen lexicographer or a citizen semantic ontologist take over, right? And that's what the GIS people did. To great effect, right? You give it up and say, everyone input, and look what happens. So, yeah, that's, as I think about it, that's probably the way we're going to have to go. Yeah.
Well, may I have one, so to say, down-to-earth question concerning the linguistic input. So you assume, well, two questions actually. You assume that sentence by sentence will be on the input, and that, and I think in one point you mentioned discourse. So what kind of discourse? Representation or influence of discourse relations?
Yeah, it's a very fair question. So the people that I have working with, I'm working with, James Allen has the TRIPS system and his own dialogue management system. James and associates don't really work with the types of dialogue models that are common, really, in Europe, for example. So it would be, I don't have any interaction, basically, with, for example, SDRT or other dialogue systems, for example, the Czech traditions. But the data structures are there in the dialogue. We have settings of context. We have ways of exploiting and then offering up to the context. This is the new object that I just created, for example. This is the list or the stack of discourse objects. So there's a lot of the same things are there. But mind you, the tradition that Allen uses is more like the Gross and Seidner style discourse structures and manipulation of the stack and so on and so forth. But utilization of focus and topic, it's ripe for the picking, right? I have that plate is completely empty in terms of how this would interact with that. And that really rich work, I would think, could be done interacting with that. Because given that inherently everything you're doing is essentially creating new things in the world or taking things out, but you're changing the state, right? You know, it's a given, but you really are doing it, and you see the effects of it. It'd be, I think, important to have a discourse semantics that's actually modeling that sufficiently richly enough to account for the linguistic data, which, you know, all things in Allen's work will do that for dialogues, but it's not as rich as other models. Yes, and James will probably say that himself, you know. Yeah, that's a good question.
Okay, thank you. And another question coming from linguistic considerations. I assume that you get a disambiguated output from the parse. But if we assume that the lexical ambiguities and structural ambiguities can be solved, so what about such sentences or input, linguistic input, which is vague in the sense of the famous sentences like 5 hunters shot 3 tigers or something like that.
Yeah.
So is there something in the system which you would use for the purpose of solving
so
the
that's a
kind
really
of
fair
vagueness?
question. Quantificational disambiguation we haven't resolved to that extent. We've resolved sort of opportunistically. So here's a really interesting problem. So you have, take something like this, okay? And you've got some blocks on the table, like down here. And the command is push them together, okay? Now, if you go look at the semantics of push in one interpretation, it's literally to move it, right? And then you want to make everything together. Well, that's not what push together means, right? You can have two blocks, and you could say push them together, and I really only have to move one. I'm trying to satisfy the end state, right? So that's a question of quantification as well, because you're trying, how many blocks do I need to actually operate over in order to reach a result state such that I have a collection such that they're all together? And so we solved that by changing the semantics of push such that we're focusing on the resulting state. It doesn't answer your question for quantifier scope and how many events do I actually create if I've got 5 solicitors visiting 12 houses. But those are going to have the same kinds of operational semantic solutions that we get in quantifier studies. Probably from the discourse, you might say, in some contexts, I might have a lexical preference for this to be a narrow scope versus a wide scope. Or the clue here is that this is an inalienable indefinite, so that it's going to be taken to be a weak internal scope to the universal. So everyone raised a hand, for example. Everyone watched a movie. So you're watching a lecture versus watching a movie, right? So given the context of being on a plane, everyone watching a movie is going to have everyone being wide scope. Everyone listened to a lecture is going to probably be the wide scope on the existential. So context is going to be important. Those are ambiguous inherently, and the situation is going to have to bring the prior to determine what the scope would be. But there again, that's probably no different than what, let's say, you would do or Johann Boss would do, for example, in SemBank. But it's a problem, right? And we haven't solved it yet. Yeah.
Okay, thank you.
Yep.
So, this was a break, so to say, and some questions might have come out. Well, if not, I just want to repeat what I said at the very beginning, that we are really honored that you could accept our invitation and come to
thank you.
have a talk.
Nice
We are
I thought you
looking
were going to say you're going to repeat that I never pronounced my own name correctly.
and we are looking forward to our joint work on the project.
With Jan Hayes. That's going to be fantastic.
And we are looking forward for some further occasions to have you in Prague.
Thank you.
So thank you very much.
Thank you.
Just for the sake of the seminar, Monday is free, coming Monday, but the Monday on the no? Oh, sorry. But I'm not here, so it was a very personal view. But that doesn't mean that you shouldn't come. There would be somebody. So the week after, we have a discourse talk given by Sanders, I think. So thank you very much.